The organ sitting inside your skull right now is using itself to understand itself. Think about that for a moment. The human brain, a 3-pound universe of electrical storms, chemical cascades, and biological architecture so advanced that the most powerful supercomputers ever built still cannot replicate what it does in a single second of consciousness. You believe you know your own brain. You believe you understand how you think, how you feel, how you dream, how you remember. But by the time this documentary is finished, you will realize that almost everything you assumed about the most complex object in the known universe was incomplete, outdated, or flat out wrong. What you are about to experience is a journey through 100 of the most surprising, unsettling, and genuinely awe-inspiring facts about the human brain, facts drawn from cutting-edge neuroscience, decades of clinical research, and discoveries so recent that most of them have never appeared in any textbook you have ever read. This is not a classroom lecture. This is not a dry recitation of anatomy. This is the story of who you really are, told through the lens of the organ that makes you you. Please let us know in the comments where you are watching this video and what time you are watching it. And be sure to subscribe to the channel for future videos. Now let us begin. Right now, at this very second, your brain is generating enough electrical activity to power a small light bulb, not metaphorically, not as an exaggeration. The neurons inside your skull are firing with approximately 12 to 25 watts of electrical power. That is enough energy to illuminate a low-wattage LED bulb. Every thought you have, every sensation you process, every memory you retrieve, all of it runs on roughly the same amount of electricity as the dim nightlight in a child's bedroom. And yet, with that modest power supply, your brain is performing calculations that would require a building-sized computer consuming megawatts of energy to even attempt. The efficiency of the human brain is not just impressive. It is, by any engineering standard, physically impossible to replicate with current technology. But here is where it gets truly strange. That electrical activity does not stop when you are asleep. In fact, during certain phases of sleep, your brain is more electrically active than it is when you are wide awake, sitting at a desk, solving a math problem. When you enter REM sleep, the stage associated with vivid dreaming, your brain lights up like a city scene from orbit. The prefrontal cortex may quiet down slightly, which is why dreams often lack logical coherence, but the visual cortex, the emotional centers, the memory consolidation regions, they are working at full throttle. Your brain does not rest when you rest. It simply shifts its focus from the external world to the vast internal landscape of your own mind, and that internal landscape is staggeringly large. The human brain contains approximately 86 billion neurons. That number gets quoted often, but it is almost never truly understood. 86 billion is not just a large number. It is a number so immense that if you tried to count each neuron at the rate of 1 per second without stopping for food, water, or sleep, it would take you more than 2,700 years to finish. Every single one of those neurons is a living cell with its own metabolism, its own electrical properties, its own set of connections to other neurons. And it is those connections, the synapses, that make the number truly incomprehensible. Each neuron can form between 1,000 and 10,000 synaptic connections with other neurons. When you multiply that across all 86 billion neurons, you arrive at a number of potential connections that exceeds the number of stars in the Milky Way galaxy. Some neuroscientists estimate the total number of synapses in the adult human brain at roughly 100 trillion. Others suggest the number may be even higher. The point is this: the combinatorial possibilities of your neural network are so vast that no two human brains in the entire history of our species have ever been wired in exactly the same way. Your brain is not just unique like a fingerprint. It is unique on a scale that makes fingerprints look like mass-produced rubber stamps. This complexity begins building before you are even born. During fetal development, neurons are created at the astonishing rate of approximately 250,000 per minute. Let that number settle in. Every 60 seconds, 250,000 new brain cells are being generated inside the developing skull of a fetus. This process, called neurogenesis, peaks during the second trimester of pregnancy and results in the creation of far more neurons than the brain will ever actually use. The developing brain massively overproduces neurons and then prunes them back, eliminating the ones that do not form useful connections. It is biological excess followed by ruthless selection, a process that mirrors evolution itself, compressed into months rather than millennia. By the time a baby is born, its brain contains nearly all the neurons it will ever have, but the brain itself is far from finished. A newborn's brain weighs about 3/4 of a pound, roughly 1/4 the weight of an adult brain. Over the first few years of life, the brain undergoes explosive growth, not primarily by adding new neurons, but by forming trillions of new synaptic connections between existing ones. A 2-year-old child has approximately twice as many synapses as an adult. The toddler brain is a wildly over-connected network, buzzing with potential pathways, and over the course of childhood and adolescence, experience sculpts that network into something more efficient, more specialized, and more adapted to the specific environment in which that child is growing up. This sculpting process, synaptic pruning, is one of the most important and least understood aspects of brain development. The connections that are used frequently get strengthened and preserved. The connections that are rarely used get weakened and eventually eliminated. It is, in the most literal sense, a use it or lose it system. The language you hear as an infant, the faces you see, the textures you touch, the emotional environments you are exposed to, all of these experiences are physically shaping the architecture of your brain, determining which connections survive and which are cut away. By the time you reach adulthood, approximately half of the synapses you had as a toddler have been pruned. Your adult brain is not a more complex version of your infant brain. It is a more refined version, streamlined, specialized, and shaped entirely by the life you have lived. But here is a fact that surprises almost everyone who hears it for the first time. The human brain does not finish developing until you are approximately 25 years old. The last region to fully mature is the prefrontal cortex, the area directly behind your forehead that is responsible for decision-making, impulse control, long-term planning, and the ability to understand consequences. This is why teenagers are not simply being difficult when they make impulsive decisions or take seemingly irrational risks. Their brains are literally incomplete. The hardware required for fully mature judgment has not finished installing. The emotional centers of the brain, particularly the amygdala, mature much earlier than the prefrontal cortex, which means that for a significant portion of adolescence, young people are navigating the world with a gas pedal that works perfectly but brakes that are still under construction. And speaking of the amygdala, this almond-shaped structure buried deep in the temporal lobe is far more powerful than most people realize. The amygdala is the brain's alarm system, the region responsible for detecting threats, generating fear responses, and encoding emotional memories. When you feel a sudden spike of anxiety, when your heart rate accelerates because you heard an unexpected noise in the dark, when you instinctively recoil from a spider or a snake, that is your amygdala taking over before your conscious mind has even registered what is happening. The speed at which the amygdala operates is genuinely remarkable. Sensory information can reach the amygdala and trigger a fear response in as little as 12 milliseconds, roughly 1/80th of a second. Your conscious awareness of the stimulus does not arrive until several hundred milliseconds later. This means that your brain has already decided you are in danger and has already begun preparing your body to fight or flee before you even know what scared you. You have experienced this. Everyone has. That moment when you jump at a shadow and then, a heartbeat later, realize it was just a coat hanging on a hook. Your amygdala acted first. Your conscious mind showed up after the fact to explain what happened. This speed exists for an obvious evolutionary reason. In a world filled with predators, the organisms that reacted fastest to potential threats were the ones that survived long enough to reproduce. But in the modern world, this hair-trigger alarm system creates problems. The amygdala does not distinguish between a genuine physical threat and a perceived social threat. It responds with the same neurochemical cascade whether you are being chased by a predator or whether you are about to give a presentation to a room full of colleagues. Your palms sweat, your heart pounds, your muscles tense, your digestion shuts down. Your brain floods with cortisol and adrenaline, all because you have to stand up and talk about quarterly projections. The amygdala is fighting for your life in a situation where your life is not actually at risk. This is, in many ways, the central tragedy of the modern human brain. It was designed for a world that no longer exists. The stress response systems, the fear circuits, the threat detection mechanisms, all of them evolved to deal with immediate physical dangers in wild environments. But the brain you carry today is essentially the same brain your ancestors carried 50,000 years ago. Evolution works slowly. Culture and technology work fast. The result is a profound mismatch between the brain we have and the world we have built. Consider this: the human brain is exquisitely sensitive to social exclusion. Neuroscience research using functional MRI has demonstrated that social rejection activates the same brain regions that process physical pain. The anterior cingulate cortex and the anterior insula areas that light up when you stub your toe or burn your hand also light up when you are excluded from a group, when you are ignored, when you feel that you do not belong. To your brain, being left out of a conversation is neurologically similar to being punched in the stomach. This is not a metaphor. This is measurable brain activity. The reason is evolutionary. For most of human history, social exclusion was effectively a death sentence. Humans are not physically formidable animals. We do not have claws, fangs, thick hides, or exceptional speed. Our survival strategy was cooperation, living in groups, sharing resources, protecting one another. Being expelled from the group meant being alone in a hostile environment, and being alone in a hostile environment meant death. So the brain evolved to treat social exclusion as a serious threat, and it encoded that threat in the same neural circuitry that handles physical injury. The pain you feel when someone ignores your text message or does not invite you to a gathering is not weakness. It is 50,000 years of evolutionary programming telling your brain that isolation is dangerous. Now, here is something that connects to this in a way you might not expect. Your brain is not only sensitive to social pain, it is also remarkably influenced by the brains of the people around you. Neuroscientists have discovered what are called mirror neurons, brain cells that fire both when you perform an action and when you observe someone else performing the same action. When you watch someone reach for a glass of water, a subset of the motor neurons in your own brain fires as though you yourself were reaching for that glass. When you see someone smile, the neurons associated with smiling activate in your brain. When you watch someone in pain, your pain processing regions respond. Mirror neurons are believed to be the neurological foundation of empathy, the ability to understand and share the feelings of another person. They may also be the basis for imitation, which is one of the most powerful learning mechanisms in the human brain. Infants imitate facial expressions within hours of being born, long before they understand language, long before they have any concept of self or other. This imitative capacity is not learned, it is hardwired. The brain arrives in the world pre-equipped to connect with other brains, to model the behavior of others, and to feel, in a diluted but real way, what other people are feeling. This has profound implications for the way we experience media, entertainment, and storytelling. When you watch a character in a film go through an emotionally intense experience, your brain does not merely observe, it participates. The emotional centers of your brain respond as though the events on screen were happening to you. Your heart rate changes, your stress hormones fluctuate, your brain releases dopamine during moments of triumph and oxytocin during moments of connection. This is why fiction affects us so deeply, why we cry at movies, why we feel anxious during suspenseful scenes, why we fall in love with characters who do not exist. Our brains blur the line between observation and experience in ways we rarely appreciate. And speaking of things the brain does that we rarely appreciate, let us talk about the truly staggering amount of processing that occurs beneath the threshold of conscious awareness. You like to believe that you are in control of your thoughts, your decisions, your actions. You believe that your conscious mind is the driver and your brain is the vehicle, but neuroscience has revealed a far more humbling picture. The vast majority of what your brain does, some researchers estimate as much as 95%, happens unconsciously. You are not aware of it, You do not direct it. You often do not even know it is happening. Your brain is at this very moment regulating your heart rate, your breathing, your body temperature, your blood pressure, your hormone levels, your immune responses, your digestive processes, and thousands of other physiological functions without any input from your conscious mind. But it goes far beyond basic housekeeping. Your unconscious brain is also processing visual information, filtering sensory input, consolidating memories, monitoring your environment for threats, generating emotional responses, and most controversially, making decisions before your conscious mind is even aware that a decision is being made. This last point deserves special attention because it challenges one of the most fundamental assumptions we hold about ourselves. In the 1980s, a neuroscientist named Benjamin Libet conducted a series of experiments that shook the foundations of how we understand free will. Libet asked participants to perform a simple task, to flex their wrist whenever they felt the urge to do so, while he monitored their brain activity using electroencephalography. What he found was startling. The brain showed a distinctive spike of electrical activity, called the readiness potential, approximately half a second before the participants reported feeling the conscious urge to move. In other words, the brain had already begun preparing the movement before the person was aware of having decided to move. This finding has been replicated and extended by numerous researchers in the decades since, and it raises profound questions about the nature of consciousness and free will. If your brain initiates an action before you consciously decide to perform it, then who is really making the decision? Is your sense of having made a choice simply a story your conscious mind tells itself after the fact, a narrative constructed to maintain the illusion of control? These are questions that neuroscience alone cannot answer, and they bleed into philosophy, ethics, law, and religion. But the underlying data is clear. Your brain does far more than you realize, and your conscious experience is a much smaller slice of your total brain activity than you have ever imagined. Let us shift now to one of the brain's most remarkable capabilities, its ability to change itself. For most of the 20th century, the prevailing scientific view was that the adult brain was essentially fixed. You were born with a certain number of neurons, they formed their connections during childhood, and by adulthood, the structure of your brain was set in stone. If neurons died, they were gone forever. If connections were lost, they were lost permanently. The adult brain was viewed as a magnificent but static machine. This view was spectacularly wrong. Beginning in the 1990s, a revolution in neuroscience, driven by advances in brain imaging technology, revealed that the adult brain is extraordinarily plastic. It changes its structure and function in response to experience throughout the entire lifespan. This property is called neuroplasticity, and it is one of the most important discoveries in the history of brain science. When you learn a new skill, playing a musical instrument, speaking a foreign language, juggling, typing, the structure of your brain physically changes. New synaptic connections form. Existing connections strengthen or weaken. In some cases, entire regions of the brain expand or contract based on how they are used. Brain scans of professional musicians show that the auditory cortex and the motor cortex are significantly larger and more densely connected than in non-musicians. Taxi drivers who navigate complex city streets for years show measurable enlargement of the hippocampus, the brain region associated with spatial memory and navigation. People who meditate regularly show increased cortical thickness in areas associated with attention and emotional regulation. The brain is not a fixed machine. It is a living, breathing, constantly adapting organ that reshapes itself in response to what you do, what you think, what you practice, and what you experience. And this plasticity does not disappear with age. While the brain is most plastic during childhood, it retains significant capacity for change throughout adulthood and even into old age. Stroke patients who lose the ability to speak or move can, with intensive rehabilitation, recruit other brain regions to take over the lost functions. People who go blind develop enhanced auditory and tactile processing as the visual cortex is repurposed for other sensory modalities. The brain is constantly rewriting itself, and the pen never runs out of ink. But neuroplasticity is a double-edged sword. The brain's ability to reshape itself in response to experience means that negative experiences shape the brain just as powerfully as positive ones. Chronic stress, for example, does not merely cause you to feel bad, it physically alters the structure of your brain. Prolonged exposure to cortisol, the primary stress hormone, causes the hippocampus to shrink, impairing memory formation and retrieval. At the same time, chronic stress causes the amygdala to grow larger and more reactive, making you more sensitive to threats and more prone to anxiety. Stress literally rewires the brain to become worse at remembering and better at being afraid. The brain adapts to the environment it encounters, and if that environment is chronically stressful, the adaptation serves survival at the expense of well-being. Trauma operates through a similar mechanism, but with even more dramatic consequences. Individuals who experience severe psychological trauma, particularly during childhood, show measurable structural differences in their brains compared to individuals who have not experienced trauma. The prefrontal cortex tends to be thinner and less active. The amygdala tends to be hyper-reactive. The connections between the emotional brain and the rational brain tend to be weaker. These are not personality traits. They are physical changes in the organ of the brain caused by experience, and they help explain why trauma has such long-lasting effects on behavior, emotion, and cognition. The hopeful counterpart to this finding is that neuroplasticity also means recovery is possible. The same mechanisms that allow the brain to be damaged by negative experience also allow it to be repaired by positive experience. Therapy, particularly forms of therapy that involve repeated exposure and emotional processing, can physically restructure the brain. Mindfulness practices can thicken the prefrontal cortex and calm the amygdala. New experiences, new relationships, new habits, all of these can lay down new neural pathways and weaken the old ones that were forged by trauma or stress. Healing is not just a psychological process, it is a neurological one. Now let us consider memory, one of the brain's most essential and most misunderstood functions. Most people think of memory as a recording device, something like a mental video camera that captures events and stores them faithfully for later playback. This is profoundly incorrect. Memory is not recording. Memory is reconstruction. Every time you recall a memory, your brain does not simply retrieve a stored file and play it back. Instead, it actively reconstructs the memory from fragments, pieces of sensory data, emotional associations, contextual cues, and narrative frameworks. And each time you reconstruct a memory, you subtly alter it. You add details that were not there originally. You omit details that were. You blend elements from different experiences. You are influenced by your current mood, your current beliefs, and the questions you are asked about the event. The memory you recall today is not the same memory you recalled last year, and neither of them is an accurate representation of what actually happened. This has been demonstrated in hundreds of studies. One of the most famous was conducted by psychologist Elizabeth Loftus, who showed that it is astonishingly easy to implant entirely false memories in people's minds. By using suggestive questioning techniques, Loftus was able to convince a significant percentage of her research subjects that they had experienced events that never occurred, getting lost in a shopping mall as a child, being attacked by an animal, nearly drowning. The subjects did not merely agree that these events might have happened. They genuinely believed they remembered them. They could describe details, recall emotions, and provide narrative accounts of events that were entirely fabricated. This finding has enormous implications for the legal system, for therapy, for education, and for everyday life. Eyewitness testimony, long considered one of the most powerful forms of evidence, is now understood to be deeply unreliable. Witnesses do not lie necessarily. They simply remember incorrectly, and they do so with complete confidence. The brain does not distinguish between real memories and false memories. Both feel equally vivid, equally certain, equally true. Your subjective sense of how well you remember something has almost no correlation with how accurately you remember it. The reason memory works this way is that accuracy was never its primary purpose. From an evolutionary perspective, the function of memory is not to create a perfect record of the past. It is to help you navigate the future. Your brain remembers things that are useful for prediction, patterns, threats, rewards, social dynamics. It does not waste resources on precise details that are unlikely to affect your survival. The emotional tone of a memory, whether something was dangerous or safe, rewarding or punishing, is far more important to the brain than the specific sequence of events or the color of the wallpaper. Memory is a survival tool, not a documentary. This is also why emotional memories are so much more vivid and persistent than neutral ones. The amygdala plays a critical role in modulating memory storage. When you experience something emotionally intense, whether positive or negative, the amygdala signals the hippocampus to encode that memory with extra strength and detail. This is why you can remember exactly where you were and what you were doing during a moment of personal crisis, even decades later, while you cannot remember what you had for lunch 3 days ago. The emotional memory system is designed to make sure you never forget the things that were most important to your survival. It does this remarkably well, but it does it at the expense of accuracy, because even emotionally vivid memories are subject to the same reconstruction errors as all other memories. There is another fascinating dimension of memory that most people never consider. Your brain is constantly forgetting, and it is doing so on purpose. Forgetting is not a failure of memory, it is a feature. If you remembered every single piece of sensory information you encountered every single day, your brain would be overwhelmed within hours. You would be unable to think, unable to focus, unable to distinguish important information from trivial noise. Forgetting is the brain's way of filtering, keeping what matters and discarding what does not. There's a famous case in the medical literature of a man known as Solomon Shereshevsky, studied extensively by the neuropsychologist Alexander Luria in the mid-20th century. Shereshevsky had an essentially limitless memory. He could recall lists of numbers, words, and formulas that he had been shown only once, and he could still recall them perfectly decades later. He never forgot anything, and far from being a gift, it was a profound disability. Shereshevsky was unable to think abstractly, unable to generalize from specific experiences, unable to follow conversations because every word triggered an overwhelming cascade of associated memories. He could not hold a regular job. He could not maintain normal relationships. His perfect memory made it nearly impossible for him to function in everyday life. He is the living proof that the brain's ability to forget is not a weakness. It is essential for thought, for abstraction, for sanity. Let us turn now to one of the most mysterious phenomena the brain produces, consciousness itself. Despite centuries of philosophical inquiry and decades of neuroscientific research, consciousness remains one of the greatest unsolved mysteries in all of science. We know that the brain generates conscious experience, the subjective sense of what it is like to be you, to see the color red, to feel the warmth of sunlight, to taste chocolate, to hear music. But we do not know how. We do not understand how physical processes in a biological organ, electrical impulses, chemical reactions, synaptic transmissions, give rise to the rich, vivid, subjective experience of being alive. This is known in philosophy as the hard problem of consciousness, a term coined by philosopher David Chalmers in the 1990s. The easy problems of consciousness, explaining how the brain processes information, how it integrates sensory data, how it directs behavior, are difficult but tractable. We can study them with brain scans and experiments. The hard problem is different. It asks not how the brain processes information, but why that processing is accompanied by subjective experience. Why does it feel like something to see red? Why is there an inner world of experience at all? Why are we not just biological robots processing data in the dark with no one home inside? No one has a satisfying answer. There are theories: integrated information theory, global workspace theory, higher order theories, but none of them has achieved anything close to consensus. Some neuroscientists believe that consciousness is an emergent property of complex neural networks, something that arises naturally when information processing reaches a certain level of integration and sophistication. Others believe that consciousness is a more fundamental feature of the universe, perhaps woven into the fabric of reality at the quantum level. Still others suspect that consciousness may be an illusion, not in the sense that we do not experience it, but in the sense that our experience of having a unified, continuous, coherent self may be a construction of the brain rather than a reflection of what is actually happening inside it. This last idea is supported by a remarkable body of evidence from split brain research. In the mid-20th century, surgeons developed a treatment for severe epilepsy that involved cutting the corpus callosum, the thick band of nerve fibers that connects the left and right hemispheres of the brain. The surgery was effective at reducing seizures, but it produced a side effect that no one anticipated. It revealed that the two hemispheres of the brain can operate as essentially independent conscious entities. In split-brain patients, the left hemisphere and the right hemisphere can be presented with different information, and they will respond independently. The right hemisphere might see an image that the left hemisphere cannot access, and vice versa. What is most astonishing is that the left hemisphere, which in most people is the hemisphere responsible for language, will confabulate explanations for the right hemisphere's behavior. If the right hemisphere is given an instruction to stand up and the patient stands up, the left hemisphere, which did not receive the instruction, will generate a plausible reason for standing. I felt like stretching, the patient might say, or I was going to get a drink of water. The left hemisphere does not know the real reason, but it creates a story anyway, and it believes its own story completely. This finding suggests something deeply unsettling about the nature of the self. The narrator in your head, the voice that explains your actions, that constructs your autobiography, that tells you who you are and why you do what you do, may not have access to the actual mechanisms driving your behavior. It may be a storyteller, not a decision maker, a press secretary, not a president, and the stories it tells may be convincing not because they are true, but because the brain is extraordinarily good at making its narratives feel true. Let us pivot to something equally fascinating, the relationship between the brain and the body. For a long time, the brain was treated as if it existed in isolation, a command center that sent orders to the body and received sensory reports in return. But modern neuroscience has revealed that the relationship between brain and body is far more intimate and bidirectional than anyone previously understood. Your gut, for example, contains approximately 500 million neurons, more than your spinal cord. This network of neurons is so extensive and so capable of independent function that it has been called the second brain. The gut and the brain are connected by the vagus nerve, the longest cranial nerve in the body, which carries a constant stream of information in both directions. Your gut sends signals to your brain about what you have eaten, about the state of your microbiome, about inflammation levels, and about 100 other variables. And your brain sends signals back that influence digestion, gut motility, and immune function. What makes this particularly remarkable is the growing body of evidence suggesting that gut health directly influences mental health. The trillions of bacteria living in your digestive tract, your microbiome, produce neurotransmitters, including approximately 95% of the serotonin in your body. Serotonin is one of the key chemicals involved in mood regulation, and the fact that almost all of it is produced in the gut, not the brain, has transformed our understanding of depression, anxiety, and emotional well-being. Research in animals and in early human trials has shown that altering the gut microbiome through diet, probiotics, or even fecal transplants can produce measurable changes in mood and behavior. Your mental state is not solely determined by what happens in your skull. It is influenced in very real ways by what happens in your stomach. The brain-body connection extends even further. Your immune system and your nervous system are in constant communication. When you're sick, your brain receives signals from your immune system that produce what neuroscientists call sickness behavior, fatigue, social withdrawal, reduced appetite, increased sensitivity to pain. These are not merely symptoms of illness. They They are adaptive responses orchestrated by the brain to promote healing. The brain forces you to rest, to avoid social contact that might spread infection, and to conserve energy so that resources can be directed toward fighting the pathogen. You do not choose to feel terrible when you are sick. Your brain makes that decision for you, and it does so for very good reasons. Conversely, your psychological state influences your immune function. Chronic psychological stress suppresses the immune system, making you more susceptible to infection and slowing wound healing. Loneliness, which the brain processes as a form of chronic social threat, has been shown to alter gene expression in immune cells, increasing inflammation and reducing antiviral defenses. People who are chronically lonely have immune profiles that look as though their bodies are preparing for bacterial infection from physical wounds, the kind of threats that would have been most common for an isolated individual in the ancestral environment. The brain is not just responding to the body. It is reshaping the body's defenses based on its assessment of the social environment. Here is another fact about the brain and body connection that will make you reconsider your daily habits. Physical exercise is one of the most powerful interventions for brain health ever discovered. Exercise does not merely improve cardiovascular fitness or build muscle. It directly enhances brain function in ways that no pharmaceutical drug has been able to match. When you engage in aerobic exercise, running, swimming, cycling, brisk walking, your brain releases a protein called brain-derived neurotrophic factor, or BDNF. This protein acts like fertilizer for neurons. It promotes the growth of new neurons in the hippocampus, strengthens existing synaptic connections, and protects neurons from damage and degeneration. Regular exercise has been shown to improve memory, enhance attention, speed up processing, reduce symptoms of depression and anxiety, and slow the cognitive decline associated with aging. In some studies, regular aerobic exercise has been shown to be as effective as antidepressant medication in treating mild to moderate depression, and with fewer side effects. The flip side is equally important. A sedentary lifestyle is not merely bad for your body, it is bad for your brain. Prolonged physical inactivity is associated with reduced hippocampal volume, impaired memory, increased risk of dementia, and accelerated cognitive aging. Sitting at a desk for 8 hours a day is not just a risk factor for heart disease and diabetes. It is a risk factor for brain deterioration. Your brain was built to move. It evolved in organisms that walked, ran, climbed, and navigated complex environments every day. When you deprive it of physical movement, you deprive it of one of the most potent stimuli for neural growth and maintenance. Let us now explore one of the most counterintuitive facts about the brain. It does not experience pain. The brain itself has no pain receptors. You could touch the surface of a living brain and the person would feel nothing. This is why brain surgery can be, and frequently is, performed on patients who are fully awake. Surgeons need only numb the scalp and skull. Once they reach the brain tissue itself, there is nothing to feel. Patients undergoing awake craniotomy can talk, answer questions, and even play musical instruments while surgeons probe and manipulate their exposed brain tissue. This is deeply ironic because the brain is the organ that processes all pain from every other part of the body. Every ache, every sting, every throb you have ever felt was generated not at the site of the injury, but in the brain itself. Pain is a construction of the brain, not a direct readout of tissue damage. This is why phantom limb pain is possible. Amputees can experience excruciating pain in a limb that no longer exists because the brain regions that process sensation from that limb are still active and still generating pain signals even though there is no limb to send them. It is also why the placebo effect is so powerful. When you believe that you have received an effective pain medication, even if you have actually received a sugar pill, your brain can genuinely reduce its pain processing. Brain imaging studies of placebo responders show decreased activity in pain processing regions and increased activity in endogenous opioid pathways. The brain is literally producing its own painkillers in response to the belief that relief is coming. This is not imagination. It is not weakness. It is measurable neuropharmacology triggered by expectation and belief. Now let us consider sleep, one of the brain's most essential and most neglected functions. You spend approximately 1/3 of your life asleep. That is not wasted time. That is the brain performing critical maintenance that cannot occur during waking hours. During sleep, the brain cycles through several stages, each serving different functions. During slow-wave sleep, the deep, dreamless stage, the brain consolidates declarative memories, transferring information from short-term storage in the hippocampus to long-term storage in the cortex. During REM sleep, the brain processes emotional memories, integrates new experiences with existing knowledge, and rehearses motor skills. But perhaps the most extraordinary discovery about sleep came in 2013, when researchers at the University of Rochester identified a system they called the glymphatic system. The glymphatic system is essentially the brain's waste disposal network. During waking hours, the brain's metabolic activity generates toxic byproducts, including a protein called beta amyloid, which is strongly associated with Alzheimer's disease. During sleep, particularly during deep sleep, the spaces between brain cells expand by as much as 60%, and cerebrospinal fluid rushes through these expanded channels, flushing out the toxic waste products that accumulated during the day. The brain literally cleans itself while you sleep, and if you do not get enough sleep, this cleaning process is truncated and the toxic waste accumulates. This discovery has profound implications for the link between chronic sleep deprivation and neurodegenerative disease. People who consistently sleep less than 6 hours per night show higher levels of beta amyloid accumulation in their brains compared to people who sleep 7 to 8 hours. Chronic sleep deprivation is now considered one of the most significant modifiable risk factors for Alzheimer's disease. You cannot cheat sleep. When you try, you are not just making yourself tired. You are allowing your brain to marinate in its own metabolic waste. Sleep deprivation also has immediate effects on brain function that are far more severe than most people realize. After just one night of total sleep deprivation, cognitive performance declines to a level comparable to being legally intoxicated. Attention, reaction time, decision-making, emotional regulation, all of them deteriorate dramatically. After several days of sleeping only 4 to 5 hours per night, the cumulative cognitive deficit is equivalent to being awake for 48 hours straight. And here is the most dangerous part. Sleep-deprived people consistently underestimate how impaired they are. They believe they are functioning normally even as objective tests show significant declines in performance. The brain loses its ability to accurately assess its own state when it is deprived of sleep. You are the last person to know how badly you are doing. The brain's relationship with sleep also reveals something fascinating about the nature of dreaming. Every human being dreams, including people who report that they never dream. Dreaming occurs primarily during REM sleep, and brain imaging during REM shows patterns of neural activity that are remarkably similar to waking consciousness, with the notable exception of the prefrontal cortex, which is significantly less active during dreams. This reduced prefrontal activity explains the illogical, surreal quality of dreams. The part of your brain that normally provides reality checking, logical reasoning, and critical evaluation is essentially offline. So your dreaming brain accepts absurdities without question. You can fly, your teeth can fall out, you can be in 2 places at once, and none of it seems strange until you wake up and your prefrontal cortex comes back online. The exact function of dreaming remains a subject of debate, but several leading theories have emerged. One theory proposes that dreams serve a threat simulation function, allowing the brain to rehearse responses to dangerous scenarios in a safe environment. This would explain why so many dreams involve themes of being chased, falling, or facing examinations. Another theory suggests that dreams facilitate creative problem solving by forming novel associations between disparate memories and ideas. There is historical evidence for this. Numerous scientific discoveries and artistic breakthroughs have been attributed to insights that occurred during dreams. The molecular structure of benzene, the melody of Yesterday by the Beatles, elements of Mary Shelley's Frankenstein, all reportedly emerged from the dreaming brain. A third theory proposed by neuroscientist Matthew Walker suggests that REM dreaming serves a critical emotional processing function. During REM sleep, the brain replays emotionally charged memories while the stress-related neurochemical norepinephrine is suppressed. This allows the brain to process the emotional content of the memory without re-experiencing the full stress response. In essence, REM dreaming may strip the emotional charge from difficult memories, allowing you to remember what happened without reliving the emotional intensity. This is why a problem that felt devastating at night often feels more manageable in the morning. You did not merely sleep on it. Your dreaming brain actively processed and diffused the emotional payload. This theory also has implications for understanding post-traumatic stress disorder. In PTSD, this emotional processing mechanism appears to be disrupted. Sufferers relive traumatic memories with full emotional intensity, both in waking life and in dreams. The dreams associated with PTSD, often vivid, terrifying, and repetitive, may represent the brain's failed attempt to process and deactivate the emotional charge of the traumatic memory. The REM processing system keeps trying and keeps failing, resulting in a cycle of re-traumatization that can persist for years or even decades. Let us now turn to the question of intelligence, a concept that the human brain is remarkably good at discussing, but remarkably poor at defining. For most of the 20th century, intelligence was treated as a single, measurable quantity, a number that could be captured by an IQ test and used to rank individuals from least to most cognitively capable. This view was always controversial, and modern neuroscience has revealed it to be dramatically oversimplified. The human brain does not have a single intelligence center. Cognitive ability is distributed across multiple brain regions and depends on the integrity and efficiency of the connections between them. Working memory depends heavily on the prefrontal cortex. Spatial reasoning involves the parietal lobes. Language processing is distributed across several regions in the temporal and frontal lobes. Emotional intelligence, the ability to read social cues, manage emotions, and navigate interpersonal relationships, depends on a network that includes the amygdala, the insula, the orbitofrontal cortex, and the anterior cingulate cortex. What we call intelligence is not one thing. It is many things, running on different neural substrates, developing at different rates, and influenced by different genetic and environmental factors. A person can be a mathematical genius and emotionally illiterate. A person can be a gifted communicator and struggle with spatial reasoning. A person can have exceptional memory and terrible judgment. The brain does not come in grades. It comes in profiles, unique constellations of strengths and weaknesses that resist simple ranking. And here is something that surprises many people. Brain size has very little to do with intelligence. The human brain ranges in size from about 1,100 to nearly 1,700 cubic centimeters, and within this range, there is no meaningful correlation between brain volume and cognitive ability. Albert Einstein's brain was actually slightly smaller than average. Some of the largest brains ever recorded belonged to individuals with no particular intellectual distinction. What matters is not the size of the brain, but the density and efficiency of its connections, the architecture, not the acreage. This is also true across species. Elephants have brains that are 3 to 4 times larger than human brains. Sperm whales have the largest brains of any animal, weighing nearly 18 pounds. Yet neither elephants nor whales exhibit the kind of abstract reasoning, language, or technological innovation that humans do. What distinguishes the human brain is not its absolute size, but the relative size of its cerebral cortex, particularly the prefrontal cortex, and the density and complexity of its interconnections. The human brain is not the biggest brain. It is the most intricately wired. There is also a surprising relationship between intelligence and mental health that deserves attention. Several large-scale studies have found correlations between high cognitive ability and increased risk of certain mood disorders, particularly anxiety and depression. This does not mean that being smart makes you mentally ill. But it does suggest that the same neural characteristics that enhance cognitive performance, heightened sensitivity to stimuli, increased cortical excitability, more elaborate processing of information, may also predispose individuals to overthinking, rumination, and excessive emotional responsiveness. The brain that is best at analyzing the world may also be the brain that is most burdened by what it finds. Let us move to one of the most fascinating areas of current neuroscience research, the brain's default mode network. When you are not actively engaged in a task, when you are daydreaming, letting your mind wander, staring out a window, your brain does not shut down. It activates a specific network of regions known as the default mode network, or DMN. This network includes the medial prefrontal cortex, the posterior cingulate cortex, the precuneus, and parts of the temporal lobe. It is called the default mode because it represents the brain's baseline state, what the brain does when it has nothing else to do. The default mode network is associated with self-referential thought, thinking about yourself, your past, your future, your relationships, your identity. It is the network that activates when you engage in introspection, when you plan, when you reminisce, when you imagine hypothetical scenarios. It is in many ways the network of the self. Abnormal activity in the default mode network has been linked to several mental health conditions. In depression, the DMN tends to be hyperactive, trapping individuals in cycles of self-referential rumination, obsessive thinking about the self, about failures, about perceived inadequacies. In anxiety disorders, the DMN generates persistent worry about future threats. In contrast, meditation practices, particularly mindfulness meditation, have been shown to reduce activity in the default mode network, which may explain why meditation is effective in reducing rumination and improving emotional well-being. The discovery of the default mode network also overturned a long-held assumption in neuroscience, that the brain conserves energy whenever possible. In fact, the brain is metabolically voracious at all times. The default mode network consumes nearly as much energy as the brain uses during focused, effortful cognitive tasks. Your brain accounts for only about 2% of your body weight but consumes approximately 20% of your total energy intake. And it consumes this energy continuously, regardless of whether you are working on a complex problem or staring blankly at a ceiling. The brain is never idle, it is always working. The only thing that changes is what it is working on. This metabolic demand has another surprising consequence. Your brain is extremely sensitive to fluctuations in blood sugar. Because the brain runs almost exclusively on glucose, unlike muscles, which can burn fat and protein, even small drops in blood sugar can impair cognitive function, mood, and self-control. Research has shown that judges are significantly more likely to grant parole immediately after a meal break than immediately before one. Students perform better on tests when they have eaten recently. People make riskier financial decisions when they are hungry. The brain's dependence on glucose means that your cognitive and emotional state is directly influenced by when and what you last ate. Your willpower is not unlimited. It runs on sugar. Now here is something that might challenge your sense of reality itself. The world you perceive, the colors, sounds, textures, and spatial arrangements that make up your conscious experience, is not an accurate representation of external reality. It is a model, a simulation, a best guess constructed by your brain from incomplete sensory data and filled in with assumptions, predictions, and prior expectations. Consider color. Color does not exist in the external world. What exists is electromagnetic radiation of different wavelengths. Your eyes detect a tiny fraction of this radiation, a band of wavelengths between roughly 400 and 700 nanometers, and your brain translates these wavelengths into the subjective experience of color. Red, blue, green, these are not properties of the physical world. They are experiences generated by your brain. An object that you perceive as red is not inherently red. It is simply reflecting light at a wavelength that your brain has learned to label as red. Other species with different photoreceptors would perceive the same object entirely differently or not at all. Sound works the same way. What exists in the physical world is vibration, pressure waves in the air. Your ear converts these pressure waves into electrical signals, and your brain transforms those signals into the experience of sound. The chirp of a bird, the crash of thunder, the voice of someone you love, none of these sounds exist in the air. They exist only in your brain. If a tree falls in a forest and no brain is there to process the pressure waves, there is vibration, but there is no sound. Sound is a brain event, not a world event. Your brain's construction of reality goes even further than this. It actively fills in gaps in sensory information to create a seamless perceptual experience. The most dramatic example of this is your blind spot. Each of your eyes has a region on the retina where the optic nerve exits the eye and no photoreceptors are present. This creates a gap in your visual field, a spot where you literally cannot see anything. But you are never aware of this gap because your brain fills it in, extrapolating from the surrounding visual information to create the illusion of a continuous visual field. You do not notice the gap because your brain has papered over it with a plausible guess, and this is not the only gap your brain fills in. Your visual system receives detailed, high-resolution information only from the small central area of your visual field, the fovea, which covers about 2 degrees of visual angle, roughly the width of your thumb held at arm's length. Everything outside this tiny central area is processed with much lower resolution. But you do not perceive a sharp center surrounded by a blurry periphery because your brain constructs a detailed panoramic visual scene from the limited data it receives, supplemented by memory, expectation, and educated guesswork. You move your eyes approximately 3 times per second, rapid movements called saccades, and during each saccade, your vision is effectively suppressed. You are functionally blind for a significant portion of every minute you are awake. But you do not notice these moments of blindness because your brain stitches together the still frames captured between saccades into a smooth, continuous visual narrative. Your experience of seeing a smooth, unbroken visual world is a masterful illusion created by a brain that has evolved to prioritize useful perception over accurate perception. This principle extends to every aspect of your sensory experience. Your brain does not show you the world as it is. It shows you a version of the world that is useful for survival. It simplifies, categorizes, predicts, and fills in gaps, and it does all of this so seamlessly that you mistake its constructed model for reality itself. You live inside a simulation generated by your own brain, and you have no access to the raw data from which that simulation is built. This brings us to something deeply related: attention. Your brain's capacity for conscious processing is remarkably limited. Despite its vast computational power, your brain can only consciously attend to a tiny fraction of the information flowing through it at any given moment. The rest is filtered out, processed unconsciously, if at all, by the brain's attentional systems. The most dramatic demonstration of this is a phenomenon called inattentional blindness. In the most famous experiment on this topic, participants were asked to watch a video of people passing a basketball and to count the number of passes. While they were focused on this task, a person in a gorilla suit walked through the middle of the scene, faced the camera, thumped its chest, and walked away. Approximately half of the participants did not see the gorilla. It was not that they saw it and forgot. They literally did not perceive it. Their attentional systems had designated the gorilla as irrelevant to the counting task and filtered it out of conscious awareness entirely. This experiment and the many studies that followed it reveals something profound about the nature of perception. You do not see everything that is in front of you. You see what your brain decides is relevant based on your current goals, expectations, and attentional priorities. The world you consciously experience is a curated selection, not a comprehensive survey, and the curation is happening without your knowledge or consent. Attention is also deeply connected to the brain's reward system, and this is where things get particularly relevant to modern life. The neurotransmitter dopamine, which is often described as the pleasure chemical, is more accurately described as the anticipation chemical. Dopamine is released not when you receive a reward, but when you anticipate one. It is the chemical of wanting, not having. It drives seeking behavior, the urge to check your phone, to click the next video, to open the next email, to scroll just a little further. Modern technology, particularly smartphones and social media, has been engineered to exploit the dopamine system with surgical precision. Variable reward schedules, the unpredictable delivery of likes, comments, messages, and notifications are the most potent drivers of dopamine release and compulsive behavior. Slot machines use the same principle. You pull the lever not because you expect to win, but because you might win, and that possibility triggers a dopamine surge that drives you to pull the lever again. Every time you pick up your phone to check for notifications, you are pulling a lever. The consequences for the brain are significant. Chronic overstimulation of the dopamine system leads to tolerance. You need more stimulation to achieve the same level of reward. It also impairs the prefrontal cortex's ability to regulate impulses and sustain focused attention. Researchers have found that heavy smartphone users show reduced gray matter volume in areas of the brain associated with cognitive control, and that the average human attention span has declined measurably over the past 2 decades. The brain is not designed for the information environment we have created. It is adapting, but the adaptations are not all beneficial. And here's a sobering fact that connects many of the themes we have explored so far. Loneliness is as dangerous to the brain and body as smoking 15 cigarettes a day. This is not an exaggeration. Meta-analyses involving hundreds of thousands of participants have found that chronic loneliness and social isolation increase the risk of premature death by approximately 26%, comparable to the risk increase associated with obesity and physical inactivity. The mechanisms involve the brain's stress response systems. Loneliness triggers chronic activation of the hypothalamic pituitary adrenal axis, which increases cortisol levels, promotes systemic inflammation, disrupts sleep, impairs immune function, and accelerates cognitive decline. The human brain is a social organ. It was designed to exist in connection with other brains. When that connection is missing, when the brain perceives itself to be isolated, it enters a state of chronic physiological threat that degrades nearly every system in the body. This is not a psychological preference. It is a biological imperative. Your brain needs other people the way your lungs need oxygen. As we approach the midpoint of this journey through the human brain, let us pause and consider what we have learned. The brain is not what you thought it was. It is not a passive recorder of experience, but an active constructor of reality. It is not a fixed structure, but a constantly changing organ shaped by everything you do and everything that happens to you. It is not a rational decision maker, but a pattern recognition machine driven largely by unconscious processes and emotional imperatives forged by evolution. It does not show you the world as it is, but creates a useful simulation and presents it as truth. It is simultaneously the most powerful information processing system in the known universe and a fragile biological organ vulnerable to stress, sleep deprivation, poor nutrition, social isolation, and the relentless overstimulation of the digital age. And we are only halfway through. The human brain has so many more secrets to reveal, secrets about language and music, about addiction and creativity, about aging and resilience, about the strange boundary between sanity and madness, about the extraordinary things the brain can do when it is damaged, and about the even more extraordinary things it can do when it is whole. All of that lies ahead. But for now, let this much settle into the organ that is processing these words. The 3 pounds of tissue inside your skull are the most complex, most mysterious, and most powerful object in the known universe. And you carry it with you everywhere you go, using it every second of every day, and yet you barely know it at all. If you stayed through the first half of this journey, your brain has already begun changing, not metaphorically, physically. The neurons processing these words have formed new synaptic connections, strengthened existing pathways, and subtly altered the electrochemical landscape of your cortex. You are not the same person you were an hour ago, not philosophically, not poetically, but neurologically. Every experience changes the brain, and this experience is no exception. In the first half, we explored the brain's architecture, its development, its relationship with the body, the illusions it creates, the memories it constructs, the consciousness it generates, and the vulnerabilities it carries from an evolutionary past that no longer matches the world we live in. Now we go deeper, into language and music, into addiction and creativity, into madness and genius, into the aging brain and the dying brain. Into the frontiers of neuroscience, where the questions become so profound that science and philosophy merge into something that neither discipline can navigate alone. Let us begin with language, arguably the single most extraordinary thing the human brain does. Every language on Earth, every one of the roughly 7,000 languages currently spoken by human beings, is produced and comprehended by essentially the same neural architecture. The brain regions involved in language are remarkably consistent across cultures, across geographies, across millennia of divergent cultural evolution. Broca's area, located in the left frontal lobe, is critical for the production of speech, the ability to form words, construct sentences, and execute the complex motor sequences required to articulate sounds. Wernicke's area, located in the left temporal lobe, is critical for the comprehension of speech, the ability to understand the meaning of words and sentences. These two regions are connected by a thick bundle of nerve fibers called the arcuate fasciculus, and together they form the core of the brain's language network. But here is what makes language truly extraordinary from a neuroscientific perspective. No other species has anything remotely comparable. Other animals communicate, birds sing. Whales vocalize, bees dance, primates use gestures and calls, but no animal other than the human being combines a finite set of meaningless sounds into an infinite set of meaningful sentences using recursive grammatical rules. This capacity, what linguists call discrete combinatorial infinity, is unique to humans, and it appears to depend on neural circuits that exist only in the human brain. The speed at which the brain processes language is staggering. During a normal conversation, you hear speech at a rate of approximately 150 to 160 words per minute. For each word, your brain must identify the sound pattern, match it against a mental dictionary of tens of thousands of words, extract the meaning, integrate it with the words that came before, generate predictions about the words that will come next, assess the speaker's emotional tone and intention, and formulate your own response, all in real time, with a delay of only a few hundred milliseconds. You do this effortlessly, without conscious effort, while simultaneously tracking the speaker's facial expressions, monitoring the social context, and occasionally thinking about what you're going to have for dinner. The computational demands of a simple conversation are almost incomprehensible, and yet every neurologically typical human being performs this feat thousands of times a day without ever appreciating how remarkable it is. Children acquire language with an ease and speed that has baffled scientists for decades. By the age of 6, the average child has a vocabulary of approximately 13,000 words and has mastered the fundamental grammatical rules of their native language, all without formal instruction, without textbooks, without grammar drills. Children do not learn language the way they learn math or history. They absorb it. They extract patterns from the speech they hear, test hypotheses about grammatical rules, and self-correct errors, all unconsciously, all automatically, and all during a developmental window that appears to have a biological time limit. This time limit, the critical period for language acquisition, is one of the most striking demonstrations of the brain's developmental programming. Children who are exposed to language during the first few years of life acquire it naturally and fluently. Children who are deprived of language exposure during this critical window, due to extreme neglect, isolation, or other tragic circumstances, often struggle to acquire full language competence even with intensive later intervention. The brain's capacity to absorb and organize language appears to depend on neural mechanisms that are maximally active during early childhood and that diminish significantly after puberty. The most heartbreaking evidence for this comes from cases of extreme childhood isolation. A girl known in the literature as Jeannie was discovered in 1970 in a state of severe neglect. She had been confined to a small room and denied almost all social contact and language exposure for the first 13 years of her life. Despite years of intensive rehabilitation, Jeannie never acquired normal language. She learned individual words but could not master grammar, the system of rules that allows words to be combined into meaningful sentences. Her case, along with similar cases, suggests that the brain's language acquisition machinery has an expiration date. If the machinery is not activated during the critical period, it may never function at full capacity. This critical period phenomenon also explains why learning a second language as an adult is so much harder than learning a first language as a child. The adult brain can certainly learn new languages, but it does so using different neural mechanisms, more conscious, more effortful, more dependent on the prefrontal cortex and explicit memory systems. The child's brain, by contrast, absorbs language through implicit, procedural learning systems that operate below the level of conscious awareness. This is why children raised in bilingual households typically speak both languages with native fluency, while adults who study a second language for years often retain a detectable accent and make grammatical errors that no native speaker would make. And speaking of bilingualism, here is a fact that has generated enormous interest in recent neuroscience research. Being bilingual changes the structure and function of the brain in measurable ways. Bilingual individuals show increased gray matter density in areas associated with executive function, including the prefrontal cortex and the anterior cingulate cortex. They also show enhanced performance on tasks that require cognitive flexibility, attentional control, and the ability to switch between competing demands. The reason is straightforward. A bilingual brain must constantly manage two active language systems, suppressing one while activating the other, and this continuous exercise strengthens the neural circuits involved in cognitive control. Most remarkably, bilingualism appears to delay the onset of dementia symptoms by an average of 4 to 5 years. This does not mean that bilingualism prevents Alzheimer's disease or other neurodegenerative conditions. The underlying pathology progresses at the same rate, but the bilingual brain appears to have greater cognitive reserve, a larger buffer of neural capacity that allows it to continue functioning normally even as disease damages the underlying tissue. The bilingual brain compensates for damage more effectively than the monolingual brain, and the result is a measurable delay in the appearance of clinical symptoms. Learning a second language is not just a cultural enrichment, it is a form of neural insurance. Now let us transition from language to something that the brain processes in ways that are both similar to and profoundly different from language: music. Music activates more areas of the brain simultaneously than any other human activity that has ever been studied. When you listen to music, your auditory cortex processes the sounds. Your motor cortex responds to the rhythm. Even if you're sitting perfectly still, your motor system is engaged, which is why you feel the urge to tap your foot or nod your head. Your prefrontal cortex tracks the structure of the piece, anticipating what comes next. Your limbic system, the emotional core of the brain, responds to the harmonic and melodic content, generating feelings of tension, resolution, joy, sadness, or triumph. Your visual cortex may activate if the music triggers mental imagery. Your memory systems retrieve associations, the song that was playing when you had your first kiss, the lullaby your mother sang, the anthem that played at a moment of personal triumph. No other stimulus engages the brain this broadly and this deeply. And the emotional power of music is not merely subjective, it is neurochemical. Listening to music you enjoy triggers the release of dopamine in the nucleus accumbens, the same brain region and the same neurotransmitter involved in the pleasure of eating, sex, and addictive drugs. Brain imaging studies have captured the exact moments when dopamine is released during music listening, and they correspond precisely to the moments that listeners identify as the most emotionally intense. The moment a melody resolves, the moment a chorus arrives, the moment an unexpected harmonic shift catches you off guard. What makes this particularly fascinating is that music is, from a survival perspective, useless. It does not provide calories, shelter, protection, or reproductive advantage. It does not help you find food or avoid predators. And yet every human culture that has ever existed has produced music. Archaeological evidence suggests that humans have been making music for at least 40,000 years. Bone flutes dating to that era have been found in caves in what is now Germany. Some researchers believe that music may be even older than language, that rhythmic vocalizations and percussive sounds may have been among the earliest forms of social bonding in our species. The brain's response to music also has therapeutic applications that are only beginning to be fully explored. Music therapy has been shown to reduce anxiety, lower blood pressure, decrease cortisol levels, and improve outcomes in patients recovering from stroke, surgery, and traumatic brain injury. Perhaps the most striking clinical application involves patients with Alzheimer's disease. Even in advanced stages of dementia, when patients have lost the ability to recognize family members, form new memories, or carry on a conversation, they can often still respond to familiar music. They can sing along to songs they knew decades ago. They can tap rhythms. They can show emotional responses, smiling, crying, swaying, that they are unable to produce in any other context. The reason is that musical memories appear to be stored in brain regions that are among the last to be affected by Alzheimer's pathology. The supplementary motor area, the cerebellum, and parts of the basal ganglia, regions involved in procedural memory and motor coordination, are relatively preserved even as the hippocampus and cortex deteriorate. Music accesses these preserved regions, bypassing the damaged ones, and for a few minutes, a person who has been lost to dementia can return to something resembling their former self. It is one of the most moving phenomena in all of neuroscience. Let us now enter one of the darkest and most important territories of brain science: addiction. Addiction is not a moral failing. It is not a lack of willpower. It is not a choice in any meaningful sense of the word. Addiction is a brain disease, a chronic, relapsing disorder that fundamentally alters the structure and function of the brain in ways that hijack decision-making, impair self-control, and create compulsive behaviors that persist even in the face of devastating consequences. The neuroscience of addiction centers on the brain's reward system, a circuit that connects the ventral tegmental area, the nucleus accumbens, and the prefrontal cortex. This system evolved to reinforce behaviors that promote survival: eating, drinking, social bonding, sexual reproduction. When you engage in one of these behaviors, dopamine is released in the nucleus accumbens, producing a sense of pleasure and motivation that encourages you to repeat the behavior. Under normal circumstances, this system works beautifully. It drives you toward the things you need to survive and thrive. Addictive substances hijack this system by flooding the nucleus accumbens with dopamine at levels far beyond anything that natural rewards can produce. Cocaine, for example, increases dopamine levels in the nucleus accumbens by approximately 350%. Methamphetamine increases them by over 1,000%. These levels of dopamine produce intensely pleasurable experiences that the brain was never designed to handle, and they trigger a cascade of adaptations that constitute the core of addiction. First, the brain downregulates its dopamine receptors. Because the drug produces such an overwhelming dopamine signal, the brain reduces the number of receptors available to receive dopamine, attempting to restore chemical balance. The result is tolerance. The user needs more of the drug to achieve the same effect. But the reduction in dopamine receptors also means that natural rewards, food, social interaction, exercise, accomplishment, now produce less pleasure than they did before. The addicted brain has recalibrated its reward threshold, and everyday life becomes flat, joyless, and unbearable without the drug. This is not weakness, it is neurochemistry. Second, the prefrontal cortex, the brain's center for judgment, impulse control, and long-term planning, is progressively impaired by chronic drug use. Brain imaging studies of addicted individuals show reduced activity and reduced gray matter volume in the prefrontal cortex. The very brain region that would be needed to make the decision to stop using drugs is the region most damaged by the drugs themselves. Addiction undermines the neural infrastructure of self-control, creating a vicious cycle in which the impaired brain is the one being asked to repair itself. Third, the brain's stress systems become sensitized. As addiction progresses, the withdrawal state, the period between drug uses, becomes increasingly aversive. The brain's stress hormones elevate, anxiety increases, sleep deteriorates, and the user experiences physical and psychological discomfort that can only be relieved by taking the drug again. At this stage, drug use is no longer driven by the pursuit of pleasure. It is driven by the avoidance of pain. The addicted person is not chasing a high. They are fleeing from a low that their own brain is creating. This understanding of addiction has profound implications for treatment and for society. Punishing people for being addicted is, from a neuroscientific perspective, as irrational as punishing people for having diabetes. Both conditions involve biological systems that have been disrupted by a combination of genetic vulnerability and environmental exposure. Both require medical treatment, behavioral change, and sustained support. Neither can be resolved by willpower alone. From addiction, let us move to something that might seem unrelated but shares deep neural roots: creativity. The creative process, the generation of novel ideas, the production of original art, music, literature, and scientific insight, has been the subject of intense neuroscientific investigation, and the findings challenge many popular assumptions. The most persistent myth about creativity is that it is a right brain function. You have almost certainly heard the claim that the left brain is logical and analytical, while the right brain is creative and intuitive. This is false. It is one of the most widespread neuromyths in popular culture, and it has no basis in neuroscience. Brain imaging studies of people engaged in creative tasks show activation in both hemispheres, distributed across multiple brain regions, with extensive communication between them. Creativity is not localized in one hemisphere. It is a whole brain phenomenon that depends on the dynamic interplay of multiple neural networks. Three networks appear to be particularly important for creative thought. The default mode network, which, as we discussed earlier, is active during mind-wandering, daydreaming, and self-referential thought, is involved in the generation of novel ideas and the free association of concepts. The executive control network, centered in the prefrontal cortex, is involved in evaluating those ideas, refining them, and determining which ones are worth pursuing. The salience network, which includes the anterior insula and the anterior cingulate cortex, acts as a toggle between the other two networks, detecting promising ideas and shifting the brain from generation mode to evaluation mode. Highly creative individuals appear to have stronger than average connectivity between these three networks. Their brains are better at switching fluidly between the open, exploratory mode of the default mode network and the focused, critical mode of the executive control network. They are better at generating a large number of ideas and then selecting the best ones. Creativity, in other words, is not just about having ideas. It is about having a brain that can move efficiently between imagination and judgment, between dreaming and doing. This has implications for how we think about creative environments and creative practices. Activities that promote mind-wandering, walking, showering, driving familiar routes, engaging in repetitive manual tasks, tend to enhance creative ideation because they activate the default mode network. This is why so many people report having their best ideas in the shower or during a walk. The brain, freed from the demands of focused attention, enters a free associative mode in which disparate concepts are combined in novel ways. The shower does not make you creative. It gives your default mode network room to operate. Conversely, chronic stress, excessive busyness, and constant digital stimulation suppress the default mode network by keeping the brain in a perpetual state of externally directed attention. If the brain never gets a chance to wander, it never gets a chance to create. The relentless productivity culture that dominates modern professional life may actually be counterproductive in precisely the domains where innovation matters most. The brain needs downtime not because it needs to rest, but because downtime is when some of its most important work gets done. Sleep also plays a critical role in creativity, and this connects back to our earlier discussion of dreaming. The associative, boundary-dissolving quality of dreams, the way the dreaming brain combines images, narratives, and concepts that would never be linked during waking thought, appears to facilitate the kind of remote associations that underlie creative insight. Studies have shown that people perform better on creative problem-solving tasks after a period of REM sleep than after an equivalent period of wakefulness or non-REM sleep. The dreaming brain is not merely processing the day's experiences. It is experimenting with new combinations, testing new patterns, and occasionally producing the kind of unexpected connection that, upon waking, feels like a breakthrough. Now let us explore one of the most unsettling territories in brain science: what happens when the brain goes wrong. Neurological and psychiatric disorders offer a window into the brain's function precisely because they show what happens when specific systems fail. And some of the conditions that result are so bizarre, so counterintuitive, and so revealing that they challenge our most basic assumptions about identity, perception, and reality. Consider Capgras syndrome. Individuals with this condition believe that someone close to them, a spouse, a parent, a child, has been replaced by an identical-looking imposter. They recognize the person's face. They can see that the person looks exactly like their loved one. But they feel no emotional connection when they see the face, and they interpret this absence of feeling as evidence that the person is a fraud. The neurological basis of Capgras syndrome involves a disconnection between the brain's face recognition system, located in the fusiform face area of the temporal lobe, and the brain's emotional processing system, centered in the amygdala and limbic structures. The face is recognized, but the emotional tag that normally accompanies recognition is missing. And rather than concluding that something is wrong with their own brain, the patient concludes that something is wrong with the other person. This reveals something profound about the role of emotion in identity recognition. You do not recognize people you love solely by their appearance. You recognize them by the feeling their appearance produces. When the feeling is absent, the recognition feels incomplete, and the brain generates an explanation, however bizarre, to account for the discrepancy. Consider also hemispatial neglect, a condition that typically occurs after damage to the right parietal lobe. Patients with hemispatial neglect lose awareness of the left side of space. They do not merely have difficulty seeing things on their left, they lose the concept of left altogether. They eat food only from the right side of their plate. They shave only the right side of their face. They draw clocks with all the numbers crowded onto the right half. If asked to describe a familiar room from memory, they describe only the objects on the right side. And here is the most disturbing aspect: they are typically unaware of their deficit. They do not know that they are missing half the world. The brain's model of reality has simply excluded the left side, and because the model feels complete, the patient has no sense that anything is missing. This condition illustrates a principle that applies far beyond the clinical realm. You cannot perceive what your brain does not represent. If a brain region responsible for constructing awareness of a certain aspect of reality is damaged or inactive, that aspect of reality does not simply become dim or unclear. It vanishes entirely from your conscious experience, and you do not notice its absence. This raises the uncomfortable possibility that even neurologically typical brains may be missing aspects of reality that they are simply not equipped to represent, dimensions of experience that we cannot perceive and cannot even conceive of, because the neural hardware required to construct awareness of them does not exist in the human brain. Another extraordinary neurological condition is synesthesia, a phenomenon in which stimulation of one sensory modality automatically triggers an experience in another. People with synesthesia might see colors when they hear music, taste shapes, feel textures when they read words, or perceive numbers and letters as inherently colored. For a synesthete, the number 5 might always be blue, the letter might always be red, and the sound of a trumpet might produce a vivid sensation of orange. Synesthesia is not imagination or metaphor. It is a genuine perceptual experience produced by cross-activation between brain regions that are normally separate. Brain imaging studies show that synesthetes who see colors in response to sounds show activation in the visual cortex when they hear sounds, activation that does not occur in non-synesthetes. The condition appears to result from atypical neural connectivity, extra connections between sensory regions that create a blending of perceptual experiences. Synesthesia occurs in approximately 4% of the population and tends to run in families, suggesting a genetic component. It is also significantly more common among artists, musicians, and writers, which has led some researchers to speculate that the enhanced connectivity underlying synesthesia may also contribute to the cross-modal thinking and rich associative processes that characterize creative ability. Whether or not this hypothesis is correct, synesthesia demonstrates that the brain's construction of perceptual reality is not fixed and universal. Different brains can construct genuinely different perceptual worlds from the same sensory input. Let us now consider the extraordinary phenomenon of savant abilities, cases in which individuals with significant cognitive or developmental disabilities display astonishing talent in a narrow domain. The most well-known examples involve prodigious mathematical calculation, calendar calculation, musical performance, artistic reproduction, and memorization. Some savants can tell you the day of the week for any date in history. Some can play a complex musical piece after hearing it a single time. Some can draw a detailed, architecturally accurate cityscape from memory after a single helicopter ride over the city. The neurological basis of savant abilities remains poorly understood, but several theories have been proposed. One influential hypothesis suggests that savant abilities emerge when damage to one brain region, typically in the left hemisphere, releases latent capabilities in other regions, typically in the right hemisphere. Under this view, the typical brain actively inhibits certain forms of low-level, detail-oriented processing in favor of higher-level, abstract processing. When the inhibitory systems are disrupted by brain damage or atypical development, the low-level processing capabilities are unleashed, resulting in extraordinary but narrow abilities. This hypothesis received dramatic support from experiments using transcranial magnetic stimulation, in which researchers temporarily suppressed activity in the left anterior temporal lobe of neurologically typical individuals. A significant percentage of these individuals showed temporary improvements in detail-oriented tasks, drawing with greater accuracy, detecting errors in text more effectively, performing mathematical estimations with more precision. The improvements were modest compared to true savant abilities, but they suggested that the typical brain may indeed be actively suppressing capabilities that are present but normally inhibited. Your brain may be capable of far more than it allows you to access, not because you have not tried hard enough, but because the brain has made a strategic decision to allocate resources elsewhere. This brings us to one of the most controversial and rapidly advancing areas of neuroscience, brain enhancement. Can we make the brain better? Can we improve memory, accelerate learning, enhance focus, or boost creativity through technological intervention? The answer, increasingly, is a qualified yes. Transcranial direct current stimulation, a technique that delivers weak electrical currents to specific brain regions through electrodes placed on the scalp, has been shown in some studies to enhance working memory, accelerate learning, and improve performance on certain cognitive tasks. Neurofeedback, a technique in which individuals learn to modify their own brain activity by observing real-time displays of their EEG signals, has shown promise in treating attention deficit disorder anxiety, and chronic pain. Pharmacological cognitive enhancers, drugs like modafinil, methylphenidate, and various nootropic compounds, are already widely used by students, professionals, and military personnel to sustain alertness, improve concentration, and enhance cognitive performance. But each of these approaches comes with caveats, limitations, and ethical questions. Enhancement in one cognitive domain often comes at the expense of another. Drugs that improve focus may impair creativity. Techniques that boost working memory may reduce cognitive flexibility. The brain operates as an integrated system, and when you push one parameter up, something else may come down. There is no free lunch in neuroscience, and the ethical questions are profound. If cognitive enhancement becomes widely available, who gets access? Does enhancement create an unfair advantage in education and employment? If you can take a pill that makes you smarter, are you obligated to do so? Are you a different person if your cognitive abilities are pharmacologically altered? These are not hypothetical questions. They are questions that society is already confronting, and they will only become more pressing as neurotechnology advances. Let us now talk about something that every human brain will eventually face: aging. The aging brain is not simply a deteriorating version of the young brain. It is a brain that has been reshaped by decades of experience, pruning, and adaptation, and while it does decline in some respects, it improves in others. The cognitive declines associated with aging are real and well documented. Processing speed decreases, the aging brain takes longer to perform mental operations. Working memory capacity shrinks, it becomes harder to hold multiple pieces of information in mind simultaneously. The ability to learn new information and form new memories declines, partly due to reduced hippocampal volume and reduced neuroplasticity. The risk of neurodegenerative diseases, Alzheimer's, Parkinson's, Lewy body dementia, increases dramatically with age, but the aging brain also possesses strengths that the young brain does not. Crystallized intelligence, the accumulated knowledge, vocabulary, and expertise that you have built over a lifetime, continues to increase well into your 60s and 70s. Emotional regulation improves with age. Older adults tend to experience less negative emotion, less emotional volatility, and greater emotional complexity than younger adults. Wisdom, a concept that is difficult to define scientifically, but that appears to involve the integration of cognitive and emotional processing, the ability to see multiple perspectives, and the tolerance of ambiguity and uncertainty, increases with age in many individuals. The brain basis of these improvements appears to involve greater integration between brain regions. While the young brain tends to show strong activation in focal, specialized regions, the older brain tends to recruit broader, more distributed networks. This has been interpreted as a compensatory mechanism. The aging brain uses more resources to accomplish the same tasks, but it may also reflect a genuine shift in cognitive strategy, from fast, focused, specialized processing to slower, broader, more integrative processing. The young brain is a specialist. The old brain is a generalist. Both have advantages, and neither is superior in all contexts. There are also factors that dramatically influence the trajectory of brain aging, and many of them are under your control. Physical exercise, as we discussed earlier, promotes neurogenesis and protects against cognitive decline. Social engagement, maintaining close relationships and participating in community activities, is strongly associated with preserved cognitive function in old age. Intellectual stimulation, reading, learning new skills, engaging in challenging cognitive activities, helps maintain synaptic density and cognitive reserve. Adequate sleep protects against the accumulation of toxic metabolic byproducts. A diet rich in omega-3 fatty acids, antioxidants, and anti-inflammatory compounds supports neuronal health. Chronic stress, conversely, accelerates brain aging by promoting inflammation and cortisol-mediated hippocampal damage. The brain you will have at 80 is not predetermined. It is, to a significant degree, the product of the choices you make at 30, 40, 50, and 60. The brain is not a candle that burns down to a stub. It is a garden that flourishes or withers depending on how it is tended. Now let us confront one of the most profound questions in all of neuroscience. What happens to the brain when it dies? For most of human history, death was defined by the cessation of the heartbeat. But with the advent of modern resuscitation technology, it became clear that the heart can be restarted and the body revived even after it has met this traditional definition of death. This forced a redefinition. Death is now defined in most medical and legal frameworks by the irreversible cessation of all brain activity, brain death. When the brain is dead, the person is dead, even if the heart continues to beat with mechanical assistance. But recent research has blurred even this seemingly clear boundary. In 2019, researchers at Yale University reported that they had restored cellular function in the brains of pigs 4 hours after the animals had been slaughtered. Using a specially designed perfusion system, they delivered a nutrient-rich solution to the dead brains and observed the resumption of cellular metabolism, oxygen consumption, and even some degree of synaptic activity. The brains did not regain consciousness. There was no evidence of organized electrical activity or awareness, but the cells themselves showed signs of viability that no one had expected to see hours after death. This experiment did not bring dead brains back to life, but it challenged the assumption that brain death is a sudden, binary event. It suggested that the brain may die not all at once, but in a gradual process, a cascade of cellular failures that unfolds over hours rather than minutes. And it raised the possibility that, with the right intervention at the right time, some of these failures might be reversible. This research has profound implications for organ transplantation, for the treatment of stroke and cardiac arrest, and for the very definition of death. If brain cells can be revived hours after the heart stops, when exactly does a person die? The answer is no longer as clear as it once seemed. There is also the strange and still unexplained phenomenon of the terminal lucidity, a burst of mental clarity that sometimes occurs in patients with severe dementia or other brain-damaging conditions shortly before death. Family members and clinicians have reported cases in which patients who had not spoken coherently in years suddenly engaged in clear, meaningful conversation in the hours or days before dying. They recognized family members, recalled memories, and spoke with an awareness and presence that had been absent for months or years. This phenomenon has been documented in the medical literature for centuries, but it remains poorly understood. If the brain tissue has been destroyed by disease, if neurons have died, if synapses have disintegrated, if the physical substrate of memory and cognition has been irrevocably damaged, how can coherent mental function temporarily return? Some researchers speculate that terminal lucidity may involve the release of neurochemicals, such as endorphins, serotonin, or norepinephrine, that temporarily enhance neural function. Others suggest that it may involve the activation of compensatory neural pathways that had been dormant. Still others admit that we simply do not know. Terminal lucidity remains one of the most mysterious phenomena associated with the dying brain, and it challenges our understanding of the relationship between brain structure and conscious experience. Let us now return to the living brain and explore a topic of enormous relevance to modern life: the neuroscience of decision-making. Every day you make thousands of decisions: what to eat, what to wear, what to say, where to go, what to buy, whom to trust. You like to believe that these decisions are rational, that you weigh the evidence, consider the options, and choose the best course of action. But neuroscience tells a very different story. The vast majority of your decisions are driven not by rational analysis, but by emotion. The neuroscientist Antonio Damasio demonstrated this through his work with patients who had damage to the ventromedial prefrontal cortex, a brain region involved in integrating emotion with decision-making. These patients had intact intelligence, intact memory, and intact reasoning ability. They could analyze options, weigh pros and cons, and articulate logical arguments, but they were catastrophically impaired in their ability to make decisions. They could not choose what to eat. They could not decide what to wear. They spent hours deliberating over trivial matters. They made disastrous financial and social decisions despite being fully aware that the decisions were bad. What they lacked was the ability to feel. Without the emotional signals that normally accompany decision-making, the gut feeling that one option is better than another, the subtle sense of unease that warns you away from a bad choice, rational analysis alone was insufficient. Damasio called these emotional signals somatic markers, and his research demonstrated that emotion is not the enemy of rational decision-making. It is the foundation. Without emotion, the brain has no basis for preference, no mechanism for assigning value, and no way to navigate the endless array of options that life presents. This finding has been replicated and extended by numerous studies. Brain imaging research has shown that when people make decisions, even decisions they believe are purely rational, the emotional centers of the brain are always active. The amygdala, the insula, the orbitofrontal cortex, and the ventral striatum all contribute to the evaluation of options and the selection of choices. The idea that you can or should make decisions without emotion is not just unrealistic, it is neurologically impossible. This also explains why marketing, advertising, and political persuasion are so effective. They do not primarily target the rational brain, they target the emotional brain. They use imagery, narrative, music, social proof, and fear to generate emotional responses that drive behavior, purchasing decisions, voting decisions, lifestyle choices, far more effectively than logical arguments ever could. Your brain is an emotional decision-making machine that uses reason as a tool, not as a master. Understanding this does not make you immune to manipulation, but it does make you aware of the mechanism by which manipulation operates. Let us now delve into one of the most rapidly evolving frontiers of neuroscience, the relationship between the brain and artificial intelligence. The human brain and modern AI systems, particularly deep neural networks, share a superficial architectural similarity. Both consist of interconnected processing units that learn from data and adjust their internal connections to improve performance. But the differences are far more significant than the similarities. The human brain processes information in parallel across billions of neurons simultaneously. It is energy efficient, consuming only about 20 watts. It is capable of generalization, learning from a small number of examples and applying that learning to novel situations. It is flexible, creative, and capable of abstract thought. It generates conscious experience. Current AI systems, by contrast, require enormous amounts of data and computational power to learn. They are narrow. An AI trained to recognize faces cannot play chess, and an AI trained to play chess cannot write poetry. They have no understanding of what they process. They have no consciousness, no subjective experience, no sense of self. They can simulate language without understanding meaning. They can produce outputs that resemble creativity without possessing anything like the internal experience of having a creative insight. But AI is advancing rapidly, and the interaction between neuroscience and AI is becoming increasingly productive in both directions. Neuroscientists use AI models to test hypotheses about how the brain processes information. AI researchers draw inspiration from neural architecture to design more efficient algorithms. And the convergence of brain-computer interface technology with machine learning is opening possibilities that were science fiction just a decade ago. Brain-computer interfaces, devices that read brain signals and translate them into commands for external devices, have already allowed paralyzed patients to control robotic arms, type text on computers, and communicate through thought alone. In recent years, the speed and accuracy of these interfaces has improved dramatically. Research participants have been able to type at speeds approaching those of able-bodied individuals using a standard keyboard by simply thinking about the movements their hands would make. The potential applications are staggering. Brain-computer interfaces could restore communication to individuals with locked-in syndrome. They could allow amputees to control prosthetic limbs with the fluidity of natural movement. They could enable individuals with spinal cord injuries to walk again using brain-controlled exoskeletons. They could, in theory, augment the cognitive capabilities of healthy individuals, enhancing memory, accelerating learning, or enabling direct brain-to-brain communication. But the ethical concerns are equally staggering. If a device can read your brain's signals, who owns that data? Can it be used against you? Can a brain-computer interface be hacked? If your cognitive abilities are augmented by a device, are you still you? If brain-to-brain communication becomes possible, what happens to privacy, to individuality, to the concept of a separate self? These are questions that the current generation of neuroscientists, engineers, ethicists, and policymakers will need to answer, and the answers will shape the future of the human species. Let us now consider something profoundly personal, the neuroscience of love. Love, romantic love, parental love, the deep attachment between close friends is not a mystical force or a purely cultural construct. It is a brain state produced by specific neural circuits and neurochemicals, and it has been studied in extraordinary detail. Romantic love activates the brain's reward system with an intensity that rivals addictive drugs. Brain imaging studies of people in the early stages of romantic love show surges of activity in the ventral tegmental area and the nucleus accumbens, the same dopamine-driven circuits involved in addiction. This is why new love produces euphoria, obsessive thinking, craving for the other person's presence, and withdrawal-like symptoms during separation. From a neurological perspective, being in love is remarkably similar to being addicted. But romantic love also involves changes in other brain systems. The neuropeptides oxytocin and vasopressin, often called the bonding chemicals, are released during physical intimacy, eye contact, and skin-to-skin contact. These chemicals promote feelings of trust, attachment, and pair bonding. They reduce activity in the amygdala, lowering fear and anxiety in the presence of the beloved. They promote the formation of long-term bonds that outlast the initial dopamine-driven euphoria of new love. Parental love involves an even more dramatic neural transformation. The birth of a child triggers a cascade of hormonal and neural changes in the parent's brain, changes that have been studied most extensively in mothers, but that also occur in fathers who are actively involved in caregiving. The brain's threat detection systems become hypersensitive to the infant's cries. The reward system is calibrated to derive intense pleasure from the infant's face and smell. The prefrontal cortex reorganizes to prioritize the child's needs above the parent's own desires. In neurological terms, becoming a parent involves a fundamental reprogramming of the brain's motivational architecture. The parent's brain is literally rewritten to ensure the survival of the offspring. And here is something remarkable. The brain changes associated with love and attachment are not permanent by default. They require maintenance. Long-term relationships that lack physical affection, shared experiences, and emotional engagement gradually lose the neurochemical reinforcement that sustains attachment. The oxytocin and vasopressin systems require ongoing activation through touch, proximity, and positive interaction. This is not a moral judgment. It is neurochemistry. The brain requires repeated input to maintain the neural pathways of love, just as it requires repeated practice to maintain any other skill. We are approaching the end of our journey now, but there are territories we must still visit. Let us talk about the brain and belief. The human brain is a belief-generating machine. It does not merely process sensory data and calculate probabilities. It constructs narratives, assigns meanings, and generates beliefs about the nature of reality, beliefs that feel absolutely certain even when they are demonstrably false. The neuroscience of belief involves many of the systems we have already discussed. The brain's pattern recognition systems are constantly searching for order in the chaos of sensory input. When they find a pattern or think they find one, the brain generates a belief to explain it. This is why humans see faces in clouds, hear messages in random noise, and find meaningful coincidences in random events. The brain is biased toward detecting patterns, even when no pattern exists. This tendency, called apophenia, is a byproduct of a pattern recognition system that is calibrated to err on the side of caution. It is better, from an evolutionary perspective, to see a pattern that is not there than to miss a pattern that is. Once a belief is formed, the brain actively works to protect it. Confirmation bias, the tendency to seek, interpret, and remember information that confirms existing beliefs while ignoring or discounting information that contradicts them, is not a personality flaw. It is a default operating mode of the brain. Brain imaging studies have shown that information that confirms existing beliefs activates the brain's reward circuits, producing a small burst of pleasure. Information that contradicts existing beliefs activates the anterior insula and the amygdala, regions associated with discomfort and threat. Changing your mind does not feel good, it feels threatening, and the brain resists it. This has enormous implications for education, politics, public health, and every domain in which changing minds is important. Presenting people with facts that contradict their beliefs does not reliably change those beliefs, and in some cases, it strengthens them. This is not because people are stupid or stubborn. It is because the brain treats its existing beliefs as part of its identity, and an attack on those beliefs activates the same defensive mechanisms as an attack on the self. Persuasion, when it works, usually operates not by overwhelming existing beliefs with contradictory evidence, but by creating emotional experiences that make new beliefs feel safe and rewarding. Let us now consider something that ties together everything we have discussed: the brain's extraordinary capacity for resilience. Despite its vulnerabilities, its sensitivity to stress, its dependence on sleep, its susceptibility to addiction and disease, the human brain possesses a capacity for recovery and adaptation that is nothing short of astonishing. Consider the cases of hemispherectomy, a radical surgical procedure in which an entire hemisphere of the brain is removed, typically to treat severe epilepsy in children. You might expect that removing half the brain would result in catastrophic disability, and in adults it would. But in young children whose brains are still highly plastic, hemispherectomy can produce remarkably good outcomes. Children who have had an entire hemisphere removed can walk, talk, learn, and go to school. The remaining hemisphere reorganizes itself to take over many of the functions normally performed by the missing hemisphere. It is not a perfect recovery. There are always deficits, but the degree of compensation is extraordinary and challenges our assumptions about how much brain tissue is truly necessary for a functional human life. Consider also the phenomenon of post-traumatic growth, the well-documented observation that many individuals who experience severe adversity, trauma, loss, life-threatening illness, report not just recovery but positive psychological transformation. They describe a deepened sense of meaning, strengthened relationships, increased appreciation for life, and a greater sense of personal strength. Brain imaging studies of individuals reporting post-traumatic growth show changes in prefrontal connectivity and default mode network activity that suggest genuine neural reorganization, not just a changed perspective but a changed brain. The brain's resilience is not unlimited, and it should not be romanticized. Not everyone who experiences adversity grows from it, and the glorification of suffering is neither scientifically warranted nor morally appropriate. But the brain's capacity to recover, to compensate, to adapt, and to transform in the face of damage and adversity is one of its most remarkable properties, and it offers genuine hope to anyone who has been told that their brain cannot change, that their condition is permanent, or that their best days are behind them. As we near the end of this journey, let us consider one final, encompassing truth about the human brain, a truth that encompasses everything we have explored and points toward everything that remains to be discovered. The brain you carry inside your skull is the most complex object in the known universe. It contains more connections than there are stars in the Milky Way. It generates its own electrical field, produces its own chemicals, creates its own reality, constructs its own identity, and contemplates its own existence. It can compose symphonies, prove mathematical theorems, build civilizations, and fall in love. It can also destroy, deceive, deny, and despair. It is capable of extraordinary compassion and extraordinary cruelty, often using the same neural circuits. And despite everything we have learned, despite decades of brain imaging, centuries of clinical observation, millennia of philosophical inquiry, we still do not understand it. We do not know how it generates consciousness. We do not know why it dreams. We do not fully understand how it stores and retrieves memories, how it makes decisions, or how it constructs the seamless perceptual reality that you are experiencing right now, at this very moment, as your eyes scan these words and your brain converts patterns of light into meaning. What we do know is this: the brain is not a finished object. It is a process. It is changing right now as it processes this information, forming new connections, strengthening some pathways, weakening others. It will be different tomorrow than it is today. It will be different in a year, in a decade, in a lifetime. Every conversation you have, every book you read, every experience you undergo, every choice you make, all of it leaves a trace in the neural landscape of your brain. You are, in the most literal sense, sculpting your own brain with every moment you live. The neuroscience of the 21st century is still in its infancy. The tools we have, functional MRI, EEG, optogenetics, single-cell recording, brain-computer interfaces, are extraordinary compared to what was available even a generation ago, but they are still crude instruments attempting to map a territory of almost inconceivable complexity. The questions that remain unanswered vastly outnumber the questions that have been resolved. And the most important questions about consciousness, about free will, about the nature of the self, may require not just better technology but entirely new ways of thinking. But here is the ultimate paradox, and it is the paradox with which we will end. Every attempt to understand the brain is itself a product of the brain. The brain is the only organ in the known universe that is trying to understand itself. Every theory about how the brain works was generated by a brain. Every experiment designed to study the brain was designed by a brain. Every conclusion drawn about the brain's nature was drawn by a brain with its own biases, its own limitations, its own blind spots, and its own constructed reality. We are trapped inside the very organ we are trying to study, looking out through windows that we built but do not fully understand, using tools that are themselves products of the thing we are trying to comprehend. This is not a reason for despair. It is a reason for humility, for wonder, and for relentless, insatiable curiosity. The human brain, your brain, is the most extraordinary achievement of 4 billion years of evolution on this planet. It is the thing that makes everything else possible. Science, art, love, language, culture, technology, philosophy, all of it exists because the brain exists. And the brain's attempt to understand itself, however imperfect, however incomplete, however fundamentally limited by the constraints of being made of the very substance it is studying, is the grandest, most ambitious, and most profoundly human endeavor there is. You began this journey believing you knew something about the organ inside your head. You have now encountered truths that should have changed that belief. Your brain is not what you thought it was. It is stranger, more powerful, more vulnerable, more creative, more deceptive, and more magnificent than any description can fully capture. It is the narrator of your life, the architect of your reality, the keeper of your memories, the generator of your dreams, and the author of your identity. And it has been doing all of this every second of every day without asking for your permission or even your attention. The next time you have a thought, any thought, pause for a moment and consider the staggering improbability of the fact that you can have a thought at all. Consider the billions of neurons, the trillions of synapses, the centuries of evolution, the decades of development, and the milliseconds of electrochemical processing that came together to produce that single, fleeting moment of consciousness. Consider that you are a brain, thinking about having a brain, marveling at the fact that a brain can think about itself at all. And then consider this: you have barely begun to understand what you are.